Lesson 19.2, Task 1, Normal Distribution. Fit a normal distribution curve to a histogram. The histogram shows the theoretical probability of getting X heads when flipping 10 fair coins. The curve shown on the histogram is a normal curve with the same mean and standard deviation as the experiment of flipping 10 fair coins. The normal curve is a smooth bell-shaped curve that represents situations where the mean is in the center of the data and the percentage decrease systematically on both sides. A normal distribution of data varies about the mean in such a way that the graph of the distribution is a normal curve. All right, so a couple definitions you need to know there. All right, so here's the normal distribution curve. You can see that it is evenly distributed about the center, which they're saying is the mean. So normal distribution curve is going to look like this in every situation. So it's going to be a similar shape. And it says, consider the situation where 20 fair coins are flipped. So this one was 10, this one is 20. So you can see that the shape is very much the same. This one has more bars, but it is still very much a normal distribution curve. So it says, how does the histogram of flipping 10 fair coins compare to the histogram represented flipping 20 fair coins? Select all that apply. Okay, so it says the histogram for flipping 10 fair coins looks more like a valley, and the histogram for 20 coins looks more like a mountain. So that's not true because they look very much the same. The histogram for flipping 20 coins has more bars than the histogram of 10 coins. So you can see that there's more bars here than there is here. So that is a correct answer. And it says because the histogram for 20 coins displays more data, the graph more closely approximates a curve. And you can see that these are a little bit closer to the line, and so that is true as well. So the more coins you flip, the little bit closer it's going to get to that normal distribution curve. And the last one says the histograms are generally the same shape. So if you look, those are both generally the same shape. So that is true as well. So that one has 3 correct answers. All right, so how do the histograms differ from the normal curves drawn on the graph? So both histograms are discrete because they stop. One has 10 coin flips and one has 20, so those both stop. That both histograms are discrete graphs that approximate the curve, but the graph with blank looks more continuous. The one with the 20 values looks a little bit more continuous because you can see here, this one looks like it stops here at 0 and 10, and this one, because it's spread out more with more numbers, it does look like it's continuous, but it's discrete between 1 and 20. All right, how would a histogram representing 100 flip fair coins be different from these? How would it compare with a normal curve? All right, so it would have more bars, it would have more information on it, but it would still represent a normal curve. All right, so the histograms show a mean of 5 and a standard deviation of 1.58 for 10 coins, and a mean of 10 and a standard deviation of 2.24 for 20 coins. Connect the changes in mean or standard deviation with the effect each has on the graph. So it says larger mean, larger standard deviation, smaller mean, smaller standard deviation. All right, so the center of the graph moves to the left. The graph narrows with no change in scale. The center of the graph moves to the right, and the graph widens with no change in scale. All right, so the graph narrows and the graph widens. So let's look at these two first. So the smaller standard deviation is going to make the graph narrow, even though there's going to be no change in scale. All right, so that means the larger standard deviation is going to affect, or it's going to widen. So the graph will widen with no change in scale. All right, so we have a larger mean and a smaller mean. So the larger mean, the center of the graph moves to the right, and it moves to the right means it's moving away from 0. So it moves to the right the larger the mean, or the larger the average gets. And the smaller the mean, the center of the graph moves to the left of the graph. All right, that's all for task 1. If you have any questions, let me know. Lesson 19.2, task 2. Find areas under a normal curve. The bell-shaped curve drawn over a histogram on the previous page are called normal curves. All normal curves can have the same basic shape. The relationship between the mean and its standard deviation remains the same for all normally distributed data sets. The relationship modeled by the area between certain intervals under a normal curve is called the empirical rule in a normal distribution. All right, so empirical rule is something that you're going to see, something that's fairly easy, but there's several things that you have to just kind of memorize. So 68% of your data is going to fall within one standard deviation of the mean. All right, so this is your mean in the middle. So it says 68% of your data will fall closest to the mean. 95% of your data will fall within 2 standard deviations of the mean. That is represented here. So you see the mean plus 1 standard deviation. Here's the mean plus 2 standard deviations. So if you go 2 standard deviations in both directions, that gives you 95%. And then 99.7% of the data falls within 3 standard deviations of the mean. So again, you can see the mean minus 3 standard deviations and the mean plus 3 standard deviations. That's 99.7% of the data. That leaves the 0.3 for outliers, etc. All right, so this is a normal distribution curve, and these percentages are standard for a normal distribution curve. So these are symbols that you need to recognize. The symbol for mean is the Greek symbol mu, and also on your calculator it's going to be labeled as X with a bar over it. So there's actually 2 different symbols you're going to see for mean. So when we look at the calculator, we're not quite there yet, but when we look at the calculator and I'll show you the steps to go through this in a little bit later. I just want you to see that this X with the bar over it is the same as mu. So this is your average, okay? This is also your average. So these are 2 symbols that represent average. This is sigma notation, Greek letter for sigma, and it is standard deviation. On here, you're going to see it's the standard deviation of X. So again, slightly different when you use your calculator. Just want you to be aware of that. Make sure that's in your notes. All right. So if you break down these percentages, if you take 68%, you know that that's plus and minus 1 standard deviation of the mean. So if you take 68 and you divide that into 2 parts, you've got 34 and 34. You take this 95%, take out the 68, and then half each side. That gives you the 13.5. Do the same for your next standard deviation, and that's where these percentages come from. You're going to use these a lot, okay? So make sure all of this is in your notes. Make sure that you are familiar with the 68, 95, and 99.7, and make sure that you can break it down even further when needed. These are easy to memorize. If you just memorize these, you should be able to calculate these very quickly, knowing that they fall within that range. All right, so the figure shows the percent of data values found in different intervals of a normal distribution with mean, mu, and standard deviation, sigma. And the first graph shows the percent with 1, 2, 3 standard deviations, and the second graph shows the percent within each interval that is 1 standard deviation wide. All right, so biologists study mountain lions in their natural habitat by sedating the animals and then collecting physical data. The lions are released back into their habitat after being revived. The mean and standard deviation for both male and female mountain lions have a long-term study are shown. From a long-term study are shown. All right, here, so we have male is 85 kilograms is the mean, and the standard deviation is 9. For females, it's 48 and 6. So what we can do is quickly make a normal distribution curve. So if we make a normal distribution curve, we know that the mean goes in the middle. So 85 goes in the middle. And then if I go 1 standard deviation to the right, I'm going to get 85 plus 9. So 85 plus 9 is 94. 2 standard deviations means I add 9 again. And then 3 standard deviations means I add 9 again. All right, now I'm going to go 3 standard deviations to the left. So I'm going to do 85 minus 9. So 85 minus 9 would be 76. And then minus 9 again would be 67. Minus 9 again is 58. So I know that the center one is 68%. The next one, 2 standard deviations, is 95%. And 3 standard deviations is 99.7%. All right. If we wanted to draw one with the female data, we could do that as well. Okay, so we can put the mean as 48. We're going to go 1, 2, 3 standard deviations, 1, 2, 3 standard deviations. Standard deviation for female is 6 kilograms. So 48 plus 6 is 54. And then 60 and 66. And then if I do 48 minus 6, I get 42. Minus 6 again, I get 36. Minus 6, I get 30. All right, so these are the normal distribution curves for the male and female mountain lions. All right, so it says, how can you use the empirical rule to determine the percent of male mountain lions that weighed between 67 and 103? What is the percent? All right, so 67 to 103, you can see that that's 2 standard deviations from the mean. All right, so we know, knowing that the mean weight for a male lion is 85 kilograms and the standard deviation is 9. I can label the graph on the normal distribution curve with the value 67 falls at the average minus 2 standard deviations, because here's the average if I do minus 2 standard deviations, and then 103 falls at the average plus 2 standard deviations. Adding the percents that fall between the values on the graph, I can see that the percent of male mountain lions weighing between 67 and 103 is 95%. Okay, so remember 68, the second one was 95. If you go out 3, it's 99.7. All right, how can you use the numbers in the figures above to determine the percent of female mountain lions between 36 and 54? So 36, we know that we're not quite all the way across. Here I'm going to have from here to 54, so it only goes 1 standard deviation to the right. So that's going to be 81.5. All right, I'm going to shut this off and continue this on the next video because I am running out of time. So that's all for this video. We'll pick back up on the next one.